The next aspect is the special properties of carbon. The carbon element is the element which forms a very large number of compounds, including organic compounds and inorganic compounds. The ability of the carbon element to form large number of compounds is due to its special properties. The special properties of carbon are the tetravalence of carbon, catenation tendency of carbon, ability of the carbon to form multiple bonds, and the last one is the strength of the chemical bonds which are formed between the atoms of the carbon element itself and with the atoms of other elements. The special properties of carbon are: the first one is the tetravalency of carbon. The second one is the catenation tendency of carbon. The third one is the ability of carbon to form multiple bonds. And the last one is the strength of the chemical bonds formed between atoms of carbon and with atoms of other elements. Other elements. These are the four special properties of carbon which has resulted the carbon element to form very large number of compounds. Let's start with the first one, which is the tetravalence of carbon. Tetravalency of carbon. What does it mean by tetravalency? Tetravalency is the ability of an atom to form four chemical bonds. So the atoms of the carbon element are able to form four chemical bonds. Before discussing the tetravalence of carbon, let's discuss first about the electronic configuration of carbon at its ground state. The electronic configuration of carbon at its ground state is: carbon has atomic number 6, or in other words, carbon has 6 electrons in its neutral form. So the electronic configuration of carbon is helium. By writing helium, we have filled 2 electrons. 2 electrons have been filled in one s orbital. But the next orbital to be filled is the next orbital to be filled is 2s orbital, which is occupied with the 2 electrons in opposite spin of direction. The next orbital to be filled is the orbitals of the sub-energy level 2p. The 2p has 3 orbitals: 2px, 2py, and 2pz. So far, we have remained with the 2 electrons. We have filled 4 electrons, 2, 2, 4. We have remained with the 2 electrons. The 2 electrons occupy the 2p orbitals according to Hund's rule of maximum multiplicity. Pairing is not allowed until each orbital is singly occupied, or until each orbital is occupied with a single electron in the same spin of direction or in parallel direction. 1, 1. This is at ground state. So at ground state of carbon, at ground state, the carbon has this electron configuration. Now, when you look careful at the electron configuration of carbon at its ground state, you will notice that there are 4 electrons in the valence shell. The valence shell of carbon is N is equal to 2, which has the 2 sub-energy levels, sub-energy level 2s and the sub-energy level 2p. The 2p sub-energy level has the 3 orbitals. So, since it has 4 electrons in its valence shell, it needs 4 electrons for it to attain the octet stable structure of noble gas elements. The octet stable structure of noble gas elements has 8 electrons in the valence shell. So since it has 4 electrons, it needs 4 electrons for it to attain the octet stable structure of noble gas elements, which has 8 electrons in the valence shell. Now, the process of carbon to gain 4 electrons in order for it to form the tetra-negatively charged gaseous ion is not possible, because this process is energetically not favored. It is energetically not possible, or it is energetically not favored because it needs a very large amount of heat energy. Very high amount of heat energy is required, which is the total electron affinity. The total electron affinity which has used to form this chemical species is very high, which cannot be compensated by the enthalpy of hydration. So this chemical species, this chemical process cannot take place in carbon. But also, when you look careful at the electron configuration of carbon at its ground state, you notice that in order for the carbon element to, in order for the carbon atom to attain the the duplet stable structure of helium, needs to lose 4 electrons. The 4 valence electrons must be lost in order for the carbon to attain the duplet stable structure of helium. But carbon needs to lose 4 electrons in order for it to attain the duplet stable structure of helium. But this process cannot take place in carbon. Why? Because this process is not energetical. It is energetically not favored. It is energetically not possible. Why? Because it needs very high amount of heat energy in order for it to be formed. The total enthalpy of ionization, which has used here, is very high, which cannot be compensated by the enthalpy of hydration. So this process cannot take place. Alternatively, carbon atom involved in the chemical bonding by electron sharing. Alternatively, carbon, party, C, 30, that is 30 in chemical bonding by electron sharing. Electron sharing is attained by overlapping of the half-filled. Electron sharing is achieved by electron sharing of the half-filled orbitals. Now, at ground state, the carbon has 2 half-filled orbitals. Or in other words, at ground state, carbon has 2 unpaired electrons. So, when carbon participates in chemical bonding at ground state by electron sharing, it tends to form 2 chemical bonds, resulting to formation of the divalent compounds of carbon. The 2 paired electrons are not involved in electron sharing. The electron sharing is achieved only by overlapping of the half-filled orbitals which contain 1 electron, like this one, and paired electrons. So, at ground state, carbon carbon forms two chemical bonds, two chemical bonds by electron sharing, by electron sharing, resulting to formation of divalent compounds like carbon monoxide gas, which are not stable. The divalent compounds of carbon are not stable. Why? Because they have high heat of formation. Any chemical species which has high heat of formation is unstable, and in most cases does not exist. For example, carbon monoxide is a divalent of carbon, which is formed when the carbon atom combine with oxygen atom at a ground state to form two chemical bonds. This chemical species is very unstable and cannot exist because it has high heat of formation. Why? This is because you have to remember that the covalent bonds, formation of the covalent bonds is an exothermic process. Since it is an exothermic process, heat energy is released to the surroundings when the covalent bond is formed. Now, the total, the amount of heat energy which is released to the surroundings depends on the number of the chemical bonds or covalent bonds being formed. If a small number of covalent bonds is formed, even the amount of heat energy released to the surroundings, it will be low. Since the amount of heat energy released to the surroundings is low due to formation of a small number of chemical bonds, the resulting compounds remain with high heat of formation. So this has high heat of formation because during its formation, a very low amount of heat energy was released to the surroundings, and the large amount of energy is, a large amount of energy remain in the compound formed as heat of formation, which is high. So any chemical species which has high heat of formation is unstable, and in most cases does not exist. But also, in order for the carbon element, carbon atom to evolve in chemical bond formation to form tetravalent compound, it needs to increase its combining power. It has to increase its combining power. The combining power is increased by promoting one of the two paired electrons from 2s orbital to the empty 2pz orbital. Now, recall electron configuration of carbon at its ground state, which is 2s, 2p, 1, 1. This is x, y, z. Now, this must increase its combining power by promoting one of the two paired electrons of 2s orbital to the empty 2pz orbital. Now, this is helium 1 electron 2s 2p is occupied with 1 electron, 1 electron, 1 electron. Now, this is at excited state. At excited state. At excited state, carbon has a total of 4 unpaired electrons. 1, 2, 3, 4. So, since it has a total of 4 unpaired electrons, when the carbon atom combines with other atoms at excited state, it tends to form a total of 4 chemical bonds by electron sharing. By electron sharing. Now, before the carbon atom combining with other atoms at excited state by electron sharing, it must undergo hybridization first. But the type of hybridization of carbon depends on the compound which is formed. For example, if the compound formed is carbon dioxide gas, if the compound formed is carbon dioxide gas has this structure. The structure of carbon dioxide gas is this. Carbon has a total of 4 chemical bonds, 1, 2, 3, 4, which are grouped into 2 groups of which are double bonds. Now, in order for the carbon to form a carbon dioxide gas, it must undergo hybridization first. But the type of hybridization depends on the kind of the chemical bond formed, or I mean the chemical bond formed or the compound formed. The number of the atomic orbitals to participate in hybridization is equal to the sigma bond. How can you know the number of sigma bonds? The number of sigma bonds is determined by just looking at the number of atoms which are connected, which are attached directly or are bonded directly to the central atom. The central atom in this case is carbon. So the number of atoms which are bonded directly to the central atom is 2. There are 2 oxygen atoms which are bonded directly to the carbon atom, which is the central atom. So the number of sigma bonds is 2, but also the number of atomic orbitals which participate in hybridization is 2. The number of sigma bonds formed is equal to the number of hybrid orbitals, or is equal to the number of atomic orbitals which participate in hybridization. So the number of orbitals which must undergo hybridization is 2, because there are 2 atoms which are directly bonded directly to the central atom. Now, after hybridization, after hybridization, carbon, this is equal to sp 2p. Now, after hybridization, one orbital from 2s is combined with one orbital from 2p. Now, 2 orbitals one from 2s and another from 2p combine to form 2 hybrid orbitals, and the 2 remaining orbitals are the unhybridized orbitals, pure unhybridized orbitals. So these are the hybrid orbitals, hybrid orbitals, and these are the unhybridized orbitals. Now then carbon, helium, to sp 2p. The set of hybrid orbitals formed is sp hybrid orbitals. 1, 1, 1, 1. Now, carbon combining with oxygen with the 2 atoms of oxygen to form carbon dioxide gas. Now, this is oxygen, this is oxygen. Now, carbon atom and the oxygen atoms combine by electron sharing. 1 electron from carbon, 1 electron from oxygen, total 2 electrons. A chemical bond is formed. Now, these are the hybrid orbitals. So when the hybrid orbitals are the ones which determine the type of hybridization of a chemical compound formed or chemical species formed. When this oxygen contributes 1 electron in the hybrid orbital, it tends to form the sigma bond. But the pi bond is formed by a fusing of by sideways fusing, or sideways overlapping of the half-filled and hybridized 2p orbitals. Half-filled, sideways. The p orbitals are dumbbell shaped. Side-by-side fusion, side-by-side fusion, or sideways fusion of the half-filled and hybridized 2p orbitals, or p orbitals. When fused together, side by side, they tend to form the pi bonds. So this oxygen atom contributes 1 electron in the unhybridized 2p orbital and hybridized half-filled 2p orbital of carbon to form the pi bond. So the pi bond is formed by the sideways overlapping of the unhybridized p orbitals. Sigma bond. You have to know that whenever there is a double bond, one is a sigma bond, while the other is a pi bond. The one is a sigma bond, while the other is a pi bond. So in carbon dioxide gas, there is a total of 2 sigma bonds and a total of 2 pi bonds. Now, one is a sigma bond, the other is a pi bond. This is a sigma bond because it is formed by overlapping of the half-filled. It is formed by overlapping of the half-filled hybridized orbitals, p orbitals. Hybridized orbitals. And this one, when contribute 1 electron in the hybrid orbital of carbon, or sp, or hybrid orbitals, it forms a sigma bond. And the pi bond is formed by a sideways overlapping of the half-filled and hybridized p orbitals. This is the pi bond. So this is the structure of the carbon dioxide gas. When you look at the structure of carbon dioxide gas, you notice that there is a total of 4 chemical bonds. 1, 2, 3, 4. A total of 4 chemical bonds. 4 chemical bonds is large in number compared to 2 chemical bonds in carbon monoxide gas. In carbon monoxide gas, or in divalent compounds of carbon. Since the number of chemical bonds formed is large, this indicates that large amount of heat energy was released to the surroundings during formation of the 4 chemical bonds. So the resulting compound remain with the low heat of formation. Now, this chemical species has low heat of formation because very large amount of heat energy was released during its formation due to formation of large number of chemical bonds. Now, since it has low heat of formation, it is stable and can exist. But the divalent compounds of carbon do not exist. Why? Because they are unstable. So once the carbon monoxide gas has been formed, it turns into carbon dioxide gas. It changes into carbon dioxide gas, which is stable. Now, this is the end of the tetravalence compound of carbon. Tetravalence compound of carbon. But also, the next one, the next special property is catenation. Catenation tendency of carbon. Catenation tendency of carbon. Catenation tendency of carbon. What does it mean by catenation? Catenation is the ability of the atoms of the same element to join, to self-join, or to join to form long chains which may be open or may be closed chains. This is the ability, catenation. Catenation is the ability of the carbon, is the ability of the atoms of the same element to join to form long chain, to form long open chain, form long open chain or closed or cyclic chain structures. Example, example, C, One, two, three, 4, 5, 6. This is the hexane. When you look at this structure, you will notice that the atoms of carbon, carbon atoms have joined together to form long open chain. This carbon has joined with this has joined with this to form long chains. Sometimes the chains are very long. The atoms combine to infinity to form very, very long chains, which are open or closed. Now, but also the chain may be closed, like this one: carbon, 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 carbon. Hydrogen, 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 hydrogen. This is the cyclobutane. Cyclobutane. The atoms of the same element, carbon atoms are the atoms of the same element, have joined together to form a cyclic structure. This is the meaning of catenation tendency. So the atoms of carbon are able of undergoing catenation due to the fact that they are small in size. The catenation tendency is attributed by small atomic size. The catenation tendency is attributed or contributed by small atomic size. The small sized atoms are the ones which undergo catenation. Why? Why is not for large sized atoms? The small sized atoms tend to catenate. This is because take an example. These are the atoms, small sized atoms. This is the nucleus of this atom, and this is the nucleus of another atom. If the atoms are small in size, the chemical bond formed is short. Since the chemical bond is short, the bond length is short because the chemical bond formed is called the bond length. The chemical bond formed, the internuclear distance, the distance from the nucleus of one atom to the nucleus of another atom is called the bond length. So it is short. Since the bond length is short, bond length is inversely proportional to the bond strength. Bond strength. As the bond length is short, the bond strength is high, or the bond energy is high. So, for the small sized atoms, when combined or joined together, they tend to form a very strong chemical bond, stable chemical bond, which can exist. So, the catenation compounds of the small sized atoms exist, but the catenation compounds of the large sized atoms do not exist. Why? Because the chemical bonds formed between the large sized atoms are unstable. They are unstable. For example, when the atoms which are combining are large in size, the bond length, the internuclear distance, bond length is large, is long, is long. The bond length, the bond length is long. Being long is inversely proportional to bond strength, or bond energy is inversely proportional to bond length. Since the bond length is long, the bond strength will be low, or the chemical the bond energy will be low. So once the catenated compounds of the large sized atoms are formed, they tend to dissociate. They tend to dissociate because the chemical bonds are weak. So the catenated compounds of large sized atoms do not exist, while the catenated compounds of small sized atoms exist because the chemical bonds formed are very stable. Now, when you look at the periodic table, 1A, 2A, 3A, 4A, 5A, 6A, 7A. Let's end up at group 7A. When you move from left to right, there is a progressive increase in atomic size. When you move, there is a progressive decrease in atomic size. When you move from left to right across the period of the periodic table, there is a progressive decrease in atomic size. The progressive decrease in atomic size is due to progressive increase in nuclear charge. The nuclear charge increases as you move from left to right due to progressive increase in number of protons. So, since the nuclear charge increases as you move from left to right, this results to a progressive increase in effective nuclear force of attraction on the electrons. So, since the effective nuclear force of attraction on electrons increases, this results to the electrons to be strongly attracted inward. Since the electrons are being attracted inward by the nuclear attractive pole, this results to contraction of electronic shells, which results to decrease in atomic size. So the atoms the atoms of elements far right in the periodic table are small in size, while the atoms of the elements far left in the periodic table are large in size. So the atoms of elements from group 1A, group 2A, group 3A, do not undergo catenation. Why? Because they are large in size. The catenated compounds of the atoms of such elements dissociate once they are formed, because their chemical bonds are very weak. So in carbon, carbon is in group 4A. The group 4A atoms are small in size. Being small in size, they can undergo catenation. So the carbon element is the element which undergoes catenation. Atoms of the carbon element undergo catenation. Why? Because they are small in size. So it was expected that for the atoms of the element of group 5A to group 7A were expected to undergo a catenation, extensive catenation, but they do not undergo extensive catenation. Why? Because why are the atoms of elements of group 5A, group 6A, and group 7A do not undergo catenation to greater extent? This is because, although they are small in size compared to carbon, they are small in size compared to the atoms of carbon, but they cannot undergo catenation like carbon atoms. Why? This is due to existence of the lone pairs. The atoms of group 5A element, group 6A element, and group 7A elements have all associated with lone pairs. Atoms of group 5A elements possess one lone pair. For example, nitrogen, phosphorus have one lone pair, but the atoms of group 6 elements possess two lone pairs. For example, oxygen atoms have two lone pairs, sulfur has two lone pairs, but also the atoms of elements of group 7A elements, fluorine, chlorine, bromine, iodine, and so forth, have three lone pairs. So there is a big repulsive force between the atoms, between the lone pairs of such atoms. Why? Due to like forces, due to like charges. You have to know that electrons are the negatively charged particles, are the particles which possess negative charge. Since are the particles which possess negative charge, according to laws of electrostatic, like charges repel each other. So when the atoms undergo catenation, when they undergo catenation, they tend the catenated compounds tend to dissociate. Why? Because the chemical bond formed between the catenated atoms is weak. It is the chemical bonds are weakened by the strong repulsive force existing between the lone pairs of those atoms. So the atoms of group 5A up to group 7A elements do not undergo catenation due to repulsive force existing between the lone pairs, which weaken the chemical bonds, and hence the chemical bonds become weak and dissociate once the catenated compounds are formed. Now, they tend to catenate to very small extent. For example, nitrogen catenated to two atoms to form nitrogen molecule. But the only atoms of such elements which have shown some extent of catenation are phosphorus and sulfur. Phosphorus atoms catenated up to 4 atoms. Catenate up to 4 atoms. Catenate up to 4 atoms. But sulfur catenating up to 80 atoms. Up to 80 atoms. 1, 2, 3, 4, 5, 6, 7, 8. They catenate up to 8 atoms. But atoms of other elements do not catenate, do not undergo catenation. That is the second one. That is the second one. The third, so carbon atoms of carbon element are the ones which undergo extensive catenation. They undergo catenation up to infinity to form very, very long chains, which are open or closed because they are small in size, but other elements do not. The third special properties of carbon is ability of carbon to form multiple bonds. The carbon atoms of carbon element are able forming multiple bonds among themselves and with atoms of other elements. The atoms of carbon element form multiple bonds among themselves and with atoms of other elements. For example, carbon forms carbon to carbon double bond, carbon to carbon triple bond, carbon to oxygen bond, double bond, carbon to nitrogen triple bond. Carbon atoms form multiple bonds among themselves and with atoms of other elements. Now, in order for the atoms to participate in multiple bond formation, they must be small in atomic size. The carbon atoms, as we have discussed earlier, are small in size. Being small in size, the first chemical bond to be formed is the single bond. For example, take this as an example. The first chemical bond to be formed is the single chemical bond, single or sigma bond. Now, then after the single bond has been formed, the second chemical bond is formed, but also even the third one can be formed if n or if necessary. Once the first chemical bond is formed, you have to know that these are the small in size. Being small in size, the nuclear attractive pole of this atom is experienced by the electron cloud of this atom. But also, the nuclear attractive pole of this atom is experienced by the electron cloud of this atom. So, the nuclear attractive pole of each atom affecting the electron cloud of another atom, of another bonded atom. Now, the nuclear, since they are small in size, the nuclear attractive pole of each atom is experienced outside. So, the electron cloud of this atom is attracted by the electron cloud, is attracted by the nuclear attractive pole of this atom, resulting to electron cloud of this to start shifting towards this atom, and the nuclear attractive pole of this atom attract the electron cloud of this atom, resulting to the electron cloud of this atom to start shifting towards this atom. Now, this results to electron sharing of the half-filled unpaired of the half-filled and hybridized two p orbitals, resulting to formation of the multiple bonds. So the second bond is formed due to the effect of the electron of the nuclear attractive poles of each atom. Now, this resulted to formation of a pi bond. The pi bonds are formed by the sideway overlapping of the half-filled and hybridized p orbitals. Now, but also even the third bond is formed like the second bond, like how the second bond is formed. That is how the multiple bonds are formed. And also, so the multiple bonds are formed due to I mean the multiple bond formation. So the multiple bond formation, multiple bond formation is due to small atomic size. But also the fourth one, the next special properties of carbon is strength is of the chemical bonds formed between atoms of carbon. I mean between strength carbon elements and other. I mean atoms of other elements. The atoms of the carbon element are able forming chemical bonds among themselves and with the atoms of other elements. They tend to form the chemical bonds. But the chemical bonds between carbon to hydrogen are very strong, which cannot be easily broken down. During chemical reactions. The chemical bonds between carbon to carbon and carbon to hydrogen bonds are very strong, which cannot be easily broken down during the chemical reactions. But the chemical bonds between carbon to other atoms of other elements are not so strong like carbon to carbon and carbon to hydrogen bond. So the carbon to atoms of other elements, apart from the element of carbon, apart from the carbon element and hydrogen element, are relatively weak, which can be broken down easily during the chemical reactions, resulting to production or to formation of a many compound. The chemical bonds bonds between the chemical bonds between atoms and between carbon atoms and atoms of other elements are not so strong. They are not so strong. Are not so strong, so they can be broken down, they can be broken down easily in chemical reactions, resulting to formation of many compounds. Formation of many compounds of many products. For example, CH3, CH2, or H. This is ethanol. And when ethanol is treated with phosphorus pentachloride reflux, it tends to form CH3, CH2, Cl plus phosphorus hypotrichloride and hydrogen chloride. The carbon to atoms of other elements are not so strong. They are less stable, so they can be broken down easily, resulting to replacement of those atoms of other elements, resulting to formation of many compounds. For example, the OH group has been replaced by the chlorine atom, resulting to formation of chloroethane.